All right, I just realized that I had not turned on the microphone, so audio is now here. Everyone that's watching the recording, you've missed an incredible YAP session. I've been saying such amazing things, incredible stuff. Nobody's lectured like me before. But now we're here, and I'm going to be perfectly mediocre. So we had talked about we've got two oxygens, so we've got 31.998 grams per mole. We've already established we're assuming that there's 1 mole of each thing, and we've got 60.052 grams. We can plug these into our mass percent formula, which is the grams of the part of the thing. In this case, that's oxygen. So we're putting our 31.998 grams of oxygen. And then the whole thing goes on the bottom, 60.052 grams of that. I don't want to write acetic acid. And then we multiply by 100%. Plug those into your calculator. You should get a number that looks pretty close to 53.28%, and that's oxygen. So a little more than half of acetic acid is just oxygen. Other stuff that we can do with formulas. We have just talked about how we can mass percent composition from a chemical formula. We can also calculate a chemical formula from mass percent composition or from mass numbers, mass values. And the formula that we get here is the empirical formula. Empirical often meaning basically experimental formula. Empirical formula also has simplest whole number ratio of the subscripts. So simplest whole number of subscripts in our empirical formula, sometimes also the molecular formula. Okay, so our empirical formula gives us the smallest whole number for each type of atom. It doesn't tell us the actual number or the specific number of each of the atoms in a molecule. It's just like what's the smallest repeating piece in the formula. Our molecular formula is to always be a whole number multiple of the empirical formula. Sometimes it's the same as the empirical formula. Okay, so an example, ethane. Ethane has the formula C2H6. Yes, C2H6. So this is the molecular formula. This is the actual formula of ethane. So that's the molecular formula. To get to the empirical formula, we're looking for the simplest whole numbers for the subscripts. So we get to do a little bit of, I think it's arithmetic. We get to do a little bit of least common denominator. So what's the smallest number that will go into both of those two numbers? Or biggest number? 2 goes into both of those. So we divide both of those by 2, we get CH3, and that would be our empirical formula. So can we simplify the subscripts? If we can, simplify until we get to something that we can't simplify, like CH3, and then that's our empirical formula. I'm pretty sure that we're going to do a lab where we calculate an empirical formula, which is good stuff, fun stuff. Okay, so let's say that we gather some experimental data. We do this science experiment. We take a sample of water, we decompose it, we produce 4.5 grams of hydrogen and 36 grams of oxygen. we can determine an empirical formula from that data. This is also, I think, something technically you could do at home, but you probably shouldn't because there's electricity involved, and oxygen and hydrogen gas are both flammable. So like things could blow up in your face, literally. But I think you can technically do this at home if you're brave enough. Okay, so the way that we would go about getting an empirical formula from that data is through this big series of steps. It's not as scary as it looks, I think. So we're going to start with the mass of each of our elements. So mass of each element present. If we're given percentages, we've got this cool trick where we turn percent into grams. We just assume that we've got 100 grams, and then the percent is the same as the grams. Or you can just remember turn percent into grams. Then we're going to convert each of those masses to moles using the molar mass. So we're going to go grams to moles, because what we're looking for in our chemical formula is the ratio of the number of things. So like how many hands per body, to give you an example of things that we can look at. How many hands per body, not the mass of hands to the mass of the body. Does that make sense? So 2 hands per body. I don't know what the mass of my hands are. That would be a freakish number for me to know. Then we divide all the moles by the smallest number of moles to get a ratio. And then sometimes we will not get a whole number, and we will not get something that's super close to a whole number. So if the moles are not whole numbers, the mole ratios are not whole numbers, then we multiply all of those moles to get whole numbers. And this is arguably the scariest part of this whole process. We've got a table over here on the right, bottom right. These are some fractional subscripts. So your number might end in 0.1, 0.2, 0.25, etc. And then over on the right are some numbers that you can multiply those by to get rid of those. So if you're really close to one of those fractional endings, then you multiply by the corresponding number over here to get to whole number subscripts. Arguably the scariest part, when we're doing stuff on exams or in class, it's typically going to work out to one of these fractional endings, so we can multiply it nicely and get a whole number. When we do it with experimental data, there's a lot more plus or minus. So we might end up being very liberal in the amount of rounding that we do. We might round up from like 0.8, for example, with a fractional ending. And then finally we write the formula using the number of moles, that's the stuff that we got from 4 or from 3, as our subscripts. Now let's take a look at what this actually looks like. Okay, we do the decomposition of water with our pencils and our little battery. We produce 4.5 grams of hydrogen, 36 grams of oxygen. We've been tasked with finding the molecular formula for water. So I like to do these in parallel. So we're going to have a couple of calculations running, a couple of lines going at the same time, and we're just going to move through each of them step by step. So we start with our grams of each. Grams of each of the elements. Then, since the mass doesn't give us information about the number of particles, we need to figure out how many particles do we have. And so moles is our proxy for that. So we're going to get to moles next. That's this step 2, go from grams to moles. So we're going to need molar masses for each of the elements. Fortunately, we've got a periodic table that tells us that. So we're going to divide by our molar masses. So the grams cancel. 4.5 divided by 1 and change. We get 4.464285714 moles hydrogen. And for our oxygen, we get a similarly long number. It's not 3, it's 2. moles oxygen. Those don't look like very nice numbers, Mr. K. You're right, those are not nice numbers. That's because we haven't done step 3 yet. Divide all the moles by the smallest number of moles. So this will get us a ratio. How many of one element do we have relative to another element? We want to divide them by the smallest, or the smaller in this case, number. Strictly speaking, you can divide by any of them, just as long as you divide them all by the same thing. If we divide by the smallest one, 2.25 and change moles of oxygen divided by that same number is going to give us our freebie, that's 1. And then this 4.46 and change for our moles of hydrogen divided by 2.25 and change, it's going to give us a number that's bigger than 1. And typically it's nicer to work with numbers that are bigger than 1 rather than working with lots of fractions or other things like that. So that's why we divide by the smaller one. So divide them all by this number. And I don't know if I've talked about the dot, dot, dot. I'm going to tell you about the dot, dot, dot. It's a real pain to write out all of those numbers. It's important that we use all the numbers, but it's a real pain to write out all those numbers. And so this dot, 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 the ellipsis, is the workaround. What the ellipsis means to me or to you, there are other numbers here. There are other numbers that follow that would be in that dot, dot, dot. We can see them just to the left of that, right? So there's other numbers that follow that, and this is the important part, we're using them. We haven't forgotten about them. We know that they're there. Our calculator has them for us. We're going to use them, but we don't want to write them all out for space or time or because our hand's cramping, which is not the case for me, but could happen. So what this means when you use this ellipsis, there are other numbers and we are using them. Okay, so new skill unlocked, the ellipsis. So now we can save ourselves tons of time. Typically, though, I would recommend writing out at least 3 or 4 numbers, especially including like however many significant figures you need. That doesn't really apply for this type of problem. Okay, so what the numbers that we're getting out from this. This is the ratio of the first number that we're dividing by the second number. So the profound thing that we're getting out with this bottom line, 2.25 and change moles of oxygen divided by that many moles of oxygen. What this is telling us is that for every 1 oxygen, we have 1 oxygen. Profound, incredible. I'm being sarcastic. I think it's just funny. For the top one, it is actually important. Okay, so we take those two numbers, we divide them, and we get 1.984 dot 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 hydrogens for every oxygen. So for every 1 oxygen that we have, we've got 1.984 hydrogens. Do you have any questions about the process so far? All right, so that was step 3. Step 4, if the moles are not whole numbers, multiply all the moles to get whole numbers. Now here comes a moment. Is this close enough to a whole number that we can just round it?
Yes.
Yes. We can just round it to 2. So 2 hydrogens for every oxygen. It's pretty close. It's quite close. We're just going to round it, because if we multiplied it, we would end up with some crazy numbers. Okay, and then we take those numbers and we make them subscripts. So 2 hydrogens, 1 oxygen, H2O. That's our empirical formula for water. Just to show you what the process looks like. All right, I can tell you all wanted to do another one, so do another one. I don't know how many I've got in the chamber, but we've got a lot. Okay, so a sample of a compound is decomposed in the laboratory and produces 34.97 grams of Fe, 15.03 grams of O. We want to calculate the empirical formula. We're going to start with the masses. So we're going to get our elements lined up here. Grams of Fe, 15.03 grams of oxygen. That's our step 1. Our step 2, we need to convert to moles. So we're going to divide by our molar masses. For iron, it's 55.85 grams per mole. So the moles is on top, the grams is on the bottom. For oxygen, it's almost 16. And plug them into our calculator. We get 0.626 ... moles Fe. We also get 0.939 ... moles oxygen. Just looks so much nicer without all those numbers. Beautiful. Okay. Now we need to find out what's the ratio of one of these to the other. Which of these are we going to divide both of them by? The smaller number. Which is the smaller number? The Fe, yeah, the 0.626. So divide both of these by 0.626 ... moles Fe. Moles Fe. The top one's a freebie. We're dividing a thing by itself. The profound result, for every one iron that we have one iron. And then the second one, which is actually important, 1.500 ... oxygens for every iron that we have. So this is our ratio of the things. To get subscripts for our chemical formula, we need whole numbers. Is 1.5 close enough to a whole number that we can round it? No, it's not. It's like smack dab right in the middle of two things. But it is really close to 1.5. So we can just call this 1.5, basically. We'll round it later. If it was 1.5, what can we multiply 1.5 by to get a whole number? 2. Right? If we multiply by 2, then that turns it into a whole number. That whole number being 3. We also have to multiply our other number by 2, even though it's just a 1. We have to change everything. You can't just do it to 1. So we get 3 for our oxygens, we get 2 for our iron. And these are our subscripts in our chemical formula. So Fe2O3 would be our empirical formula. Since you are all thinking it, we'll do another one. This is just to show you that we can do it with percentage as well, and we can do it with 3 or more chemicals too. So fluorofluoride is a fume again, pesticide that's used to treat termite infestations in houses and has the mass percent composition as follows. For sulfur, oxygen, and fluorine, calculate the empirical formula of sulfuryl fluoride. 2 of my neighbors recently had their houses fumigated. They had the, if you see houses and they've got those clown tent things around them, that's what they're doing. They're doing a sulfuryl fluoride fumigation. They also use a little bit of chloropicrin, which is there because it makes you cry. And so if you go inside, you don't just die to the sulfuryl fluoride. You smell the chloropicrin and you're like, something's bad in here. I should leave. And you hopefully get out before you perish. Anyway, all that aside, we've got some mass percent compositions. Now, this is confusing because we have been starting our problems with grams, not percent. What can we do to get from percent to grams? Magic. We just convert the percentages into grams. We assume that we've got 100 grams, and then the percentages turns into grams. So it's this one neat trick that chemistry instructors love. Okay, so for our sulfur, we've got 31.42 grams of sulfur. For our oxygen, we've got a little more than 31 grams of oxygen. A little more than 37 grams for our fluorine. We convert to moles for each of these by dividing by their molar masses. It's always the molar mass of just one of the things, by the way. We're never going to use the molar mass of F2 or O2. All right, and then we get to plug in a lot of numbers. And here are the numbers that we get. We get 0.98 ... moles sulfur. We get 1.95 and change moles of oxygen. We get 1.95 and change moles fluorine. Which of these is the smallest number? Sulfur up at the top, right? So we're going to divide all of these by our moles of sulfur. And we get one freebie. The top one we don't have to do a calculation. We don't have to put anything into our calculator. It's a number divided by itself. So we get one sulfur per sulfur. Awesome. For the other ones, we get to plug in the whole 1.95 and change divided by the whole 0.98 and change. Or, if you've got my favorite calculator, you just press the up arrow, find the number, press enter, it pulls the whole number out for you. Divide by, press the up arrow, find the whole number, hit enter, it pulls the number for you. Saves you a ton of time. If you're confused about how to do that, you want me to show you in lab, let me know. So we end up with this, 1.999 ... oxygens for every sulfur. We'll see that we get a similar thing for our fluorines. Okay, moment of truth. Are these numbers close enough that we can round them to whole numbers? Yeah. Are you sure? Yes, you better be sure. They're super close to 2. We're going to just round them to 2. It'd be ridiculous to expect things to be closer than that. Okay, so we've got 1 for our sulfur, 2 for our oxygen, 2 for our fluorine. And so we would end up with a formula that looks something like SO2F2 for our empirical formula. Questions, concerns, smart remarks? All right, then we will stop there and pick up with hydrates next class.